Hi, it's Mr. Anderson, and today I'm going to be talking about acids, bases, and then pH. Now, the picture I have here is actually a picture of lichen, which is a combination of a fungus and an algae. Now, you may be asking yourself, why do you have lichen on this page? And it's a good question. The reason why is that this is actually what we make litmus paper out of. And so litmus paper, you've maybe seen this before, comes in red and blue. Litmus paper is actually derived from certain species of lichen, and so we use it to sense the amount of acid or base in a solution. Before we talk about what acids and bases are, we should first talk about the dissociation of water. And so what does that mean? Well, water is a polar molecule. In other words, the hydrogen is going to have a positive charge, and then the oxygen is going to have a negative charge. And the reason why is that oxygen is highly negative. And so this bond right here is something called a hydrogen bond. In other words, it's a connection between this hydrogen, which has a positive charge, and this oxygen, which has a negative. And so that's what holds water molecules together. It gives water high specific heat. There's a lot of things that come out of hydrogen bonds. But one weird thing about it is that occasionally that hydrogen will actually disassociate. In other words, this hydrogen will come unattached from here, and it'll attach onto another water molecule. And so what do you get when you do that? You get something called hydronium ion. Now, in science, we rarely talk about hydronium and draw out hydronium. We normally just talk about that hydrogen coming disassociated. So we normally just talk about this H plus moving across. And so anything that increases the amount of this hydrogen ion coming unattached and forming hydronium is an acid. And anything that decreases the amount of that is actually called a base. And so what is pH? If we define what pH is first, it is the negative log of the concentration of hydrogen ions or hydronium ions. Now, the brackets here mean the concentration. And so what does that mean? It's the negative log of the molar value of hydrogen ions. So what is it in water? Well, you know that in water, the pH is going to be equal to 7. And so where did we get that value? It's the negative log of 1 times 10 to the negative 7th. Or if we write this number out as a value, it's 1 in every 10 million. Hopefully I got my numbers right. And so what does that mean? How statistically common is this, that the hydrogen pops off and actually attaches over to water? It's incredibly rare. It doesn't happen very often in water. And anything that increases that amount is going to be called a acid. So let's talk about acids and then bases. And so most famous acid, and the reason it's famous is it's really easy for me to draw it out, and it's used quite a bit in chemistry, would be hydrochloric acid. So hydrochloric acid is going to be an acid. That means its pH is going to be up in this value. Why is it an acid? Well, if you add this to water, in other words, in an aqueous solution, what's going to happen to this? This is actually going to form hydrogen ions and chloride anions. In other words, this is going to disassociate from itself. So we're going to have this hydrogen ion, and what's that going to do? It's going to increase the hydrogen ion concentration. What's that going to do to the pH? It's going to push the pH in this direction. If we look at something like a base, a quintessential base would be this sodium hydroxide. What happens with sodium hydroxide when we add it to water? It's going to break down into sodium, which has a positive charge, and hydroxide, which is going to have a negative charge. And so what a base is anything that is going to lower the concentration of H+. Well, I don't see any H pluses here. The reason why is that every time you have a hydroxide, it's going to combine with a hydrogen ion, and it's going to form something called water. And so bases, or anything that has hydroxides in it, are actually going to lower the concentration of hydrogen ions or hydronium ions. And so first let's talk about acids. Acids, and I wrote acids in red font because I always want you to remember that acids are red, are things that are going to increase the amount of hydronium ion concentration. So what is this molecule right here? This molecule is actually going to be water molecule. We've got 1 oxygen, 2 hydrogens, but it's picked up another H+. And so this is that hydronium ion. We picked up that one more hydrogen. Remember, acids are going to be anything with a pH less than 7. And so examples of things that are less than 7 would be coffee, tomato juice, all the way down to the enzymes within our stomach, which have a really low pH. The lower we go on this value, the more acidic something becomes. And so what does that mean? The farther we go down here, it's kind of backwards, the greater the concentration of H plus ions is actually going to be as we move farther down the pH. What are some other properties of acids? They tend to react with hydrogen gas. And so an example of this would be if you were to mix hydrochloric acid with zinc, that's what's right here. What it'll actually form is hydrogen gas, and then it's going to form a zinc chloride. I think I've got my balance right there. And so this hydrogen gas is going to be given off. And that's a real common property of acids. You mix them with water and you're going to get hydrogen gas from that. They also have a tendency to turn blue litmus paper red. And so what I want you to remember is that they are always red. And then they have a sour taste. Now, I have an acid with us today. This is a safe acid. This is vinegar. Vinegar is acetic acid. And so if we were to test it, let me first of all try it with red litmus paper. If I do it with red litmus paper, it's going to turn red litmus paper red, or it's going to not change the color of it. But if I were to dip blue litmus paper in vinegar, it's going to turn that blue litmus paper, I'm not sure if you can see that blue litmus paper is now going to turn red. And so that indicates an acid. One other thing that you should never do in the lab is taste acids and bases. That'd be really dangerous, but this is just vinegar. And so if I taste this, okay, that's going to be really, really sour taste. And so that's one indication of an acid. You shouldn't taste acids in the laboratory, but trust me, that's sour. And actually, that's how we make things like Sour Patch Kids. We do that by adding a lot of acids to it. Okay, let's talk about bases. Bases are going to be anything that increase the hydroxide ion concentration or increase the amount of OH. They also thereby decrease the amount of H+. These things are going to have a pH that's greater than 7. So examples would be baking soda, milk of magnesia, all the way up to soapy water. I've got one of those with us. So this is sodium bicarbonate, and you know this as baking soda. So let me taste that. If I were to taste this, oh my gosh, that tastes really bad. That's a really bitter taste. It also has kind of a slippery feel to it. I've added a lot of the sodium bicarbonate to this, and if I were to taste, kind of move my fingers around on it, it's obviously going to be slippery because it's in water, but it just feels soapy if you've got a base. So it's got this slippery kind of feel. I'm Norwegian, and one of the traditions that we like to have around holiday time, this time of the year, is we like to eat something called lutefisk, which is actually taking a fish and soaking it in lye. Lye is really, really alkaline or really, really basic, and so you then have to rinse it out really, really a ton, and so you can make it edible. But it does taste kind of slippery. It breaks down the proteins that way. Also, if we take this, and so let's go to the litmus test. This would be a base now, sodium bicarbonate. If I were to put the blue inside it, it's going to stay blue, because remember, bases are blue. But if I were to take the red litmus paper, then it should turn that towards a blue color, and it does. So it turns it blue. So we know that it's basic. And so how do you figure out if something's an acid or a base? We can just use litmus paper. If I put base in red litmus paper, it's going to turn it to blue, and vice versa when we put it in an acid. So it's going to have that opposite kind of reaction. It's always going to turn it blue. Last thing that I wanted to talk about is what makes a strong acid and what makes a strong base. Strong and weak don't really refer to the pH. You can have weak acids that have a really, really low pH, and you can have strong acids that don't have such a low pH. And so it doesn't reference that at all. If we talk about hydrochloric acid is HCl. And remember what I said is that's going to break down into H plus and Cl minus. And every one of those hydrogen and chloride ions, every one of those atoms is going to disassociate when we add it to water. In other words, it's not like a certain percentage of the hydrogen is going to break down. All of the hydrogen is going to break down. And so that would be a strong acid. Everything completely breaks down, or completely ionized. We talk about that. If we talk about something like vinegar, vinegar is CH3COOH. If I were to draw out, you may think to yourself, why does it have all the O's and H's kind of out of order here? The reason why, if we write it out, it might make a little more sense. We've got a carbon attached to these 3 hydrogens on this side, so that'd be that. We then have another carbon on this side, which is double bonded to an oxygen, and then we have an OH on this side. And so what can happen to our acetic acid? Well, it's weak, and so not all of them are going to do this, but occasionally we will lose this H+. So what does that do? That increases the amount of H+, and it's going to decrease the pH. And so it leaves behind an ionized acetic acid or acetate when it's gone, but we've increased the amount of H+. Now, why do we call that weak? The reason why is that it's really statistically rare, something like 0.4% of the time that we lose that H+, if the pH of our acetic acid is pretty low, like 2.4. So even though we may have a pH that's really low, it's rare that we're losing that hydrogen ion, and so that's why we call it a weak. If we look at bases, how do bases work? Bases, remember, a strong base would be like sodium hydroxide. Sodium hydroxide is going to break down completely into sodium and hydroxide, or OH minus, and all of the atoms in this are going to break down, and that's why we call that a strong base. This is a weak base, so it's NaHCO3. So if I were to sketch that out, it's going to be an ion of the sodium. We're then going to have a carbon, which is bonded to an oxygen, which is bonded to another oxygen, and is finally bonded to an OH. And so how does this work on sodium bicarbonate? That's what this is, which is, it's going to be regular baking soda. What happens is that this oxygen has an actual negative charge, and so it's going to grab on to an H+, and so it's going to grab on to that and actually form OH at this point. So it's going to decrease the amount of hydrogen ion concentration. And so it's not all of that is going to disassociate, or not going to grab all of those hydrogens, and that's why we would call it a weak base. So those are kind of acids and bases. You've played with these your whole life, and so if you take, you remember, a little bit of this sodium bicarbonate, and then we add a little bit of acid to it, we'll get fuzzing. And essentially what we're getting in here is we're making carbonic acid, and then we're also making a little bit of carbon dioxide. And I'll try not to spill that on my computer. So those are acids, and those are bases, and that is pH.